This reaction between potassium iodide and hydrogen peroxide is described as being a redox reaction. But exactly what do we mean by a redox reaction? Redox is a compound word made from two other words, oxidation and reduction. Oxidation is described as being combination with oxygen. For instance, when we burn magnesium in air to produce magnesium oxide, this is described as an oxidation. On the other hand, if we remove the oxygen from a metal ore, such as iron oxide, this is described as being a reduction, a removal of oxygen. Both of these processes have to occur at the same time. However, just limiting our definition to being combination or removal of oxygen is far too limiting to describe reactions that we have to look at. So we need to broaden our definition a little bit more.
When zinc metal is exposed to oxygen at high temperature, it reacts to form zinc oxide. Electrons are transferred from zinc to oxygen, creating oxide and zinc ions. We say that zinc has been oxidized. The oxidation of zinc by molecular oxygen is an example of an oxidation-reduction reaction. More generally, oxidation corresponds to a loss of electrons. Zinc is oxidized because it loses electrons to the oxygen. On the other hand, oxygen is said to be reduced because it gains electrons.
So now we have a slightly broader definition for redox. Redox is an electron transfer which has two parts to it. The oxidation is defined as being the loss of electrons, so a substance has to lose 1, 2 or maybe even 3 electrons, and at the same time something has to gain those electrons, and that's the reduction process where electrons are actually transferred from one substance to another. There's a simple mnemonic we can use to help us try and remember this. Oxidation is loss, reduction is gain, and if you take the first letters of that, that gives us oil rig. Or if you prefer a more biological one, loss of electrons is oxidation, gain of electrons is reduction. And here we have our Leo saying grrr. So let's have a look at some examples of redox reactions. If we take a piece of zinc metal and put it into copper sulfate solution, we know that the copper ions come out of solution and form a deposit of copper metal on the zinc plate. But what's actually going on? Well, first of all, the zinc dissolves into solution, forming the zinc 2+ ion, and that leaves 2 electrons, which are available for reaction. The copper 2+ ion comes out of solution, picks up those 2 electrons, and turns into copper metal. So we can write the ionic equation for the reaction as being copper 2+ plus zinc to give us copper metal and zinc 2+ ions. But what about the sulfate ion? What's the role of that? Well, as we know, the sulfate ion doesn't take part in the reaction at all, so it's just a spectator ion. But can we demonstrate that this reaction is actually a redox reaction? Let's have a look. We can simplify this reaction if we write half equations. One equation to show what the oxidation is and one equation to show what the reduction is. So if we have a look at what's happening to the copper ion is gaining electrons. In other words, if it's a gain of electrons, it's a reduction. The copper ion is being reduced. On the other hand, the zinc metal is losing electrons. The electrons appear on the right-hand side of the equation to show that they're being lost. So in this case, it's an oxidation, remembering that both reactions occur at the same time. So if we wanted to write an overall equation for this, we'd collect all the terms on the left-hand side of the arrows. So we'd have the copper 2+ and the zinc and the 2 electrons. And then on the right-hand side of the equation, we'd have copper plus zinc 2+ ions and 2 electrons again. But you can see that we've got electrons on both sides of the equation here, so they cancel out, leaving us with our overall ionic equation of copper 2+ plus zinc to give us copper metal and zinc 2+. And we've now demonstrated that this is indeed an oxidation-reduction reaction, where something has actually lost electrons and something else has gained electrons. So can we write the half equations for this reaction? The first step we need to do is to identify the substance that's actually losing the electrons or being oxidized. And if you look at this, we can see that calcium is a neutral metal, but when it's combined with calcium chloride it's going to have 2 positive charges, so this one must be the one that's actually losing electrons. So this one must be the one that's in our half equation for oxidation. So calcium forms calcium 2 plus and 2 electrons. The second step is to identify the substance that's gaining electrons, the one that's being reduced. So we're going from neutral chlorine to a chloride ion. So that must be our reduction half equation, which we'd write as Cl2 plus 2 electrons to give 2 chloride ions. You notice here that all the substances are actually involved in the reaction. And if we add those two half equations together, the 2 electrons cancel out and we get our full overall equation. Sometimes we have half equations which are a little bit more complicated to balance other than just adding electrons. You can see in this case we have the dichromate ion, and it's going to form a chromium 3 ion, and there are some oxygens involved, so the process is a little bit more complex but still relatively simple if you follow the steps. The first thing we need to do is to balance all the atoms except oxygen and hydrogen. In this case we've got 2 chromiums on the left, so we need to have 2 chromiums on the right. The second step is to balance the oxygens by using water. Most of these reactions occur in aqueous solutions, so obviously there is going to be some water present. So since we've got 7 oxygens in the dichromate ion, we need to balance it by adding 7 waters. Now of course that's introduced 14 hydrogen ions, which we have to put on the left hand side. Again, these reactions are done in water, and they can be done in acidified water, which has a little bit of H plus added, or in basic water, which has got a little bit of hydroxide, but all the reactions you'll be doing are in an acidified environment, so it's quite alright to add H plus to balance our equation. So the third step involves balancing the hydrogens by using H plus, or protons, because we are in an acidic environment. And since we need 14 of them, we can add 14 H pluses on the left hand side. Now we've got our atoms balanced, we need to look at our charge. On the left hand side we've got a total of 12 positive charges, and on our right hand side we've got 6 positive charges. So to balance the charges we need to add some electrons, and they have to go onto the left hand side, and 6 of them. And that now gives us the charge on each side of the equation being a total of positive 6. But the charges are balanced and the atoms are balanced, and now we have our completed reduction equation. Another example of this sort of balancing is the conversion of the permanganate ion into manganese 2 plus. Remembering our steps again, the first thing is to balance everything except the oxygen and hydrogen. Well, in that case we just have the manganese to balance, and in this case there's 1 on each side, so that's fine. Our second step was to balance the oxygen by adding water. We've got 4 oxygens on the left hand side, so we need to add 4 waters onto the right hand side. The third step was to balance the hydrogens by adding H+. On our right hand side we've got 8 H hydrogen atoms, and so therefore we need 8 H pluses onto the left hand side. Now when we look at our charges, we've got a total of 7 positives on the left and 2 positives on the right, so we balance our charge out by adding electrons, and in this case we need to add 5 onto the left hand side. So far we've looked at reactions where the electrons that have been produced by the metal have been consumed by the other substance, and they've exactly balanced out. But what happens if it doesn't exactly balance out, such as in the reaction between magnesium and oxygen? First thing we need to do is to look and see what substance is losing electrons, and again in this case it's the magnesium. Metals are often oxidized, and in this case the magnesium forms a magnesium 2 plus ion and 2 electrons. Therefore the oxygen must be the substance which is gaining electrons, and the half equation for the oxygen is oxygen as a molecule, 2 oxygens, plus 4 electrons to give us the 2 oxide ions. Now if you look here you can see that the oxygen wants to get 4 electrons, but the magnesium has only got 2 to give away. So in order to make our equation balance, we have to have 2 lots of magnesium actually losing electrons to give us those 4 electrons. So we have to multiply that equation of magnesium going to magnesium ions by 2. Then if we try and construct our overall equation, we add up all the substances on the left hand side of the arrow. We've had to multiply our magnesium by 2, and we add in our oxygen and the 4 electrons. And on our right hand side of the equation we've got 2 magnesium 2 plus ions, the oxide and the other 4 electrons. Now we've got our electrons exactly balanced, so they'll cancel out, and our overall ionic equation is going to be 2Mg plus oxygen to give us 2MgO. Let's have a look at another example. In this case, we've got aluminium gaining 3 electrons, but zinc can only lose 2. So we need to find out how many electrons we need to transfer in this particular case to balance them up. Looking for the lowest common denominator, we can see that if we multiply the first equation by 2 and the second equation by 3, that should give us 6 electrons to be lost and 6 electrons to be gained. When we work out our overall equation, that therefore means that we'll have 2 aluminiums plus the 6 electrons and the 3 zinc atoms on the left-hand side, and the right-hand side will be 2 aluminium, 3 zinc ions and 6 electrons. Now we have our 6 electrons, they can be cancelled out to give us our overall ionic equation.